Good day, grade 9s. I'm Miss Todd, and today's lesson will be about series and parallel electric circuits. We will be starting with a little bit of revision and then moving on to how series and parallel circuits work and the different calculations that will be used for each circuit. Let's start off with some revision. These are the components that we use to compile a circuit or to make a circuit. Firstly, we have a switch, which controls the current that flows through the circuit. Then we have cells and batteries, which are our power sources of the circuit. A light bulb is represented with a circle and a cross through it, which is our light source in our circuits. A voltmeter, which will measure the voltage flowing through the voltage of a circuit. Then we have an ammeter, which measures the current flowing through a circuit. A resistor, which controls the amount of current flowing through a circuit. And then we have a rheostat, which is a variable resistor. Lastly, we have a motor, which we can also include in a circuit. To carry on with some revision, let's go over power sources. Previously, we've discussed that batteries and cells are the main power sources that we use in a circuit. It is measured in voltage, and the unit symbol that we use is a capital V. We measure voltage using a voltmeter, but what is important is that it's connected in parallel to the component. And some revision with regards to cells. Within a cell or battery, a chemical reaction will take place, and during that reaction, the chemical energy is transformed into electric energy to flow through the circuit. With regards to current is measured in amperes, and the unit symbol that we use is a capital A. The symbol that we represent current with when we start with our calculations is capital letter I. We measure current in a circuit using an ammeter, and an ammeter will always be connected in series in a circuit. The definition of what current is the flow of an electric charge or electrons through a certain point of a circuit. With regards to resistance is measured in ohms, and the unit symbol is the omega symbol. The symbol which we represent resistance with in circuit calculations is a capital letter R. The definition of what resistance is the ability of a conducting material to control the amount of current flowing through or to provide a useful energy transfer. In other words, we explain it as the opposition that a device has against the flow of a charge, which means how easy or how hard it is for electrons to move through a device. Now remember, with resistance, the main reason as to why a device will have resistance is to provide a useful energy transfer, either in the form of electrical energy to light energy or electrical energy to kinetic energy. Let's have a look at the differences between series circuits and parallel circuits. Our first one is series circuits. Firstly, there is only one pathway for current to flow through, meaning there is only one way in which the currents can flow. The electrical current within a series circuit is equal everywhere in the circuit. So no matter where we measure the current using an ammeter, it will always be equal. The potential difference, or the voltage of the circuit, will be the sum of the voltages in the electric current, meaning the sum of all the voltmeters that are in the current, in the circuit, Then, with regards to series, the more resistors in series, the bigger the resistance, and resistors in series are potential dividers. This is due to a resistor with a higher voltage will have a higher resistance, and a resistor with a lower voltage will have a lower resistance. Now, with regards to parallel circuits will have different pathways for the current to flow through, meaning there's not just one single pathway, there could be multiple pathways for the current to flow through. The electric current therefore divides between the different parts of a circuit and will not be the same everywhere in a parallel circuit. The potential difference or the voltage in a parallel circuit is equal everywhere in the circuit, and the more resistors in parallel, the smaller the resistance as the current will increase. Lastly, because electric current divides at the different paths, resistors in parallel are known as current dividers. Now this is where we use the formulas for electric circuits, starting with series circuits. Firstly, if we were to ask you to measure current in an electric circuit, which is a series circuit, our formula would be IT is equals to I1 is equals to I2 is equals to I3. This is because the current is equal everywhere in a series circuit, and over here, IT means the total current, and it is the same as the readings on multiple ammeters found in the circuit. Our next one is potential difference or voltage. For this formula, it is VT is equals to V1 plus V2 plus V3, or depending on how many voltmeters are connected in the series circuit. VT means total voltage, and the way in which we get that is by adding all the readings of all the voltmeters connected in the circuit. So VT is adding all the readings of the voltmeters in a circuit. This is because potential difference is the sum of voltages in an electric circuit for series. With regards to resistance, our formula for resistance is RT is equals to R1 plus R2 plus R3. Again, RT is the total resistance, and we get it by adding the values of all the resistors in the circuit. Now we have a look at the formula used specifically for parallel circuits, starting with current. Current's formula, or to measure current in a parallel circuit, we use IT is equals to I1 plus I2 plus I3. Again, IT means the total current, and the way we get the current is by adding the readings of all ammeters in the circuit. This is because current divides between the different paths, so to get the total, we need to add the amounts or the readings on all the ammeters present in a parallel circuit. With regards to potential difference or voltage, the formula we use here is VT is equals to V1 is equals to V2 is equals to V3, or however many voltmeters are used in the circuit. VT means the total voltage, and it is the same as the reading on multiple voltmeters. This is because potential difference is equal in a parallel circuit. With regards to resistance, this formula is a different one compared to the others. So we have RT is equals to 1 over R1 plus 1 over R2 plus 1 over R3. But we have an extra step here. The last step after the calculation has been made, the fraction must be inverted, which means swapped around in the final step in order to get the correct value of the resistance in a parallel circuit. Now we have a look at our triangle formulas, which we are able to use for both series and parallel circuits. Our first triangle is our VIR triangle. V represents voltage, and we measure it in volts. I represents current, and we measure it in ampere. And R represents resistance, and we measure it in ohms. The way in which we use the triangle, the values or the letters on top of each other will be divided, and next to each other will be multiplied. So let's have a look. If we were to calculate voltage, voltage is V is equals to I times R. If we were to calculate current, current is I is equals to V divided by R. And if we were to calculate resistance, resistance is R is equals to V divided by I. Our second triangle is our QIT triangle. where Q represents charge and we measure it in coulombs, I represents current and we measure it in ampere, and T represents time and we measure it in seconds. Same rule applies with our dividing and our timesing. So if we want to calculate charge, charge is Q is equals to I times T. If we want to calculate current, current is I is equals to Q divided by T. And if we were to ask you to calculate time, time would be T is equals to Q divided by I. Our third triangle is our PVI triangle, where P represents power and we measure it in watts, V represents voltage and we measure it in volts, and I represents current and we measure it in ampere. Same rule applies here with our dividing and our multiplying. So if we want to calculate power, power, which is P, is equals to V times I. Voltage, if we were to calculate voltage, voltage would be V is equals to P divided by I. And if we were to calculate current, current is I is equals to P divided by V. Our fourth and final triangle, which you should familiarize yourself with this year, is our WVQ triangle, where W represents work or energy and it's measured in joules, V represents voltage and it's measured in volts, and Q represents charge and it's measured in coulombs. Again, same rule applies with our dividing and our multiplying. So if we'd like to calculate work or W, the formula we'll use is W is equals to V times Q. If we were to calculate voltage, voltage will be V is equals to W divided by Q. And if we were to calculate charge, charge will be Q is equals to W divided by V. Now let's have a look at how we will ask the questions based on a series circuit. Our first question is, calculate the total voltage of the circuit. What we mean by the total voltage is the total amount of voltage or power that is supplied to the circuit. We start off our answer by writing out what our formula is to see what is needed. Our formula is Vt is equals to V1 plus V2. We have a voltmeter reading at the top of our circuit and a voltmeter reading at the bottom of the circuit. So we will assume here that the bottom voltmeter is voltmeter reading 1 and the top voltmeter is voltmeter reading number 2. So to get the total voltage, we add the readings of the voltmeters. As you will see in this circuit, we do not have a third voltmeter, so we are just using the formula up until V2. So our answer goes like this. Vt is equals to 5V plus 4V. So the total voltage in this circuit is 9 volts. Our second question, or a second question we could ask, is to calculate the total resistance of the circuit. In this example, we are still using a series circuit. The formula that we use to calculate resistance for series is adding the resistance together. So as you can see here, we have a light bulb with a resistance of 2 ohms and another light bulb with a resistance of 3 ohms. So our formula goes like this. RT is equals to R1 plus R2 because we only have 2 resistors in this series circuit. We substitute the values from our circuit into the formula. So our next step will be RT is equals to 2 ohms plus 3 ohms, which gives us a total resistance of 5 ohms. Our third question relating to this specific circuit is what is the total current of this circuit? Now, as you can see on the circuit, there is no ammeter available. So we will need to calculate the current using the information we have. So from question 1, we determined that the total voltage is 9 volts. From our second question, we determined that the total resistance is 5 amperes. Therefore, we are able to use our VIR triangle. So in order to calculate current, our formula will be I is equals to V divided by R. Now it becomes a substitution equation. So I is equals to 9 volts divided by 5 ohms, which gives us an answer of 1.8 amperes, and that is the total current of this series circuit. Now we move on to parallel circuits and the equations and questions that can be asked about parallel circuits. So question 1 says a voltmeter, which is V1, is placed over the light bulb with the resistance of 3 ohms. What will that voltmeter reading be? So we place the voltmeter over the light bulb that has the resistance of 3 ohms. Now, with regards to parallel circuits and the formula which we use in order to calculate voltage, we have the formula Vt is equals to V1 is equals to V2 is equals to V3, or depending on the number of voltmeters present in the circuit. So, our answer here, we already have a total voltmeter reading of 6 volts. And the rule for a parallel circuit is that the voltmeter reading, or the potential difference, is equal everywhere in a circuit. So our answer here, the voltmeter reading on V1, if it is placed over light bulb with a resistance of 3 ohms, remains 6 volts. Our second question for parallel circuits is to calculate the total resistance of the parallel circuit. So we have one light bulb that has a resistance of 3 ohms, and we have a second light bulb with the resistance of 1 ohm. The formula that we use in order to calculate resistance in parallel is RT is equals to 1 over R1 plus 1 over R2 plus 1 over R3. Now, because we do not have a third resistance, we are just going to use the first 2 substitutions of this equation. So our second step would be RT is equals to 1 over R1. So we labeled this light bulb as R1 and this light bulb as R2. So RT is equals to 1 over 3 plus 1 over 1. This gives us an answer of 4 over 3. But remember the rule with regards to resistance, the fraction must be inverted in the final step of the calculation. So here we swap around the values to give us RT is equals to 3 over 4. We convert it to a decimal and our answer is 0.75 ohms, and that is the total resistance of this parallel circuit. Our third question with regards to a parallel circuit is to calculate the total current. So the information we give you in the question says the reading of ammeter A2 is 5 amperes. And the reading on ammeter A3 is 3 amperes. Calculate the total current. Now the reason why we have said the total current is A1 because it's found in the series part of the circuit. So because there is one pathway here, it will give us the total current that will split into A2 and A3. So the formula which we use in order to calculate current in parallel is IT is equals to I1 plus I2. We have put ammeter A2 as I1 and ammeter A3 as I2. Because there is no third ammeter, we can leave out I3. So our formula looks like this. IT is equals to 5A plus 3A. So the total current of this circuit is 8 amperes. A second possible way in which we can calculate the total current, which is A1, is to use the information that we've calculated previously. So we have the total voltage, which is 6 volts, and previously we calculated the total resistance. So our second possible answer could be to use our VIR triangle. The formula which we will use to calculate the total current is I is equals to V over R. V is the total voltage and R will be the total resistance. So we substituted in, so it is I is equals to 6V divided by 0.75 ohms, and it gives us an answer of 8 amperes. This is a second possible way in order to calculate total current based on what we've calculated previously in the question. Thank you for coming to my lesson, grade 9s. We'll see you next time for safety with electricity.